Welcome back, everybody. AP Chemistry, taking a look at Chapter 16. This is Unit 5 and Section 2. Expanding on the voltaic cells a little bit, we're going to focus on a couple of ideas here with those reducing and oxidizing agents. Okay, then we're going to look at strengths, and then we'll translate that into the actual electrical energy that goes along with this. Okay, so remember a couple of things along the way that when we take a look at oxidizing agents, those are things that are going to be gaining electrons. And keep in mind, I'm going to say this a lot, that we're going to be seeing that these things that are going to be gaining the electrons, these are my cathodes because they're becoming more negative. Those things then, as we take a look at the next step, those things that are going to be reducing, the agents that are involved with the reducing agents, they're going to be giving up. And remember, that means they're going to become more positive along the way. That is going to be the anode along with this. And so, again, like I said, this is your cathode. And this is my anode. We've got to wrap our mind around these concepts. So let's give an example of something that's going to be gaining electrons. In the previous section, we took a look at copper that's going to be picking up 2 electrons and becoming the copper metal. Okay, and so we said also in that one from the example from section 1, we took my zinc metal, and that's going to become my zinc ions, and it's going to be giving up those electrons. And so what happens is this thing is getting oxidized. Now here's the mind bender. This thing is getting oxidized, and so it is referred to as a reducing agent. Now, the reason we call it a reducing agent is because it gets oxidized. Oxidized. This is the thing then copper would be referred to as my oxidizing agent. Why is that? Because it gets reduced. Now, what the heck does that mean? If it's getting oxidized, that means it's going to be losing electrons. So what does that mean in terms of causing it to go? Well, it has to lose the electrons, which means that it causes that thing to pick up the electrons. It enables it to do it. So a reducing agent is the enabler of it that gets oxidized. And this thing is the oxidizing agent because it gets reduced. It wants to take in electrons. Why? Because it helps to facilitate that. It's serving as an oxidizing agent. Okay? He wants to be oxidized. He lets it happen. Okay, he allows it to do those. And so those are some of the things that you just have to keep practicing, talk yourself through, and hopefully that's a helpful example. Now, if we take a look at these different scenarios in here, and we take a look at our table from that we can look up from this chapter or whatever, we see some numbers. Okay, and it talks about these things, and we can use that standard table of the standard potentials to do some of these skills. I'm not going to go through every single one in terms of it, but we can see that we've got some number values that are associated with it. And there's a couple of ways that we can pick this thing apart. If I find my permanganate right there, I see that it has a 1.51. I see it listed in a couple places. We don't know exactly what's going on with it, but I see a 1.51 and I see a 1.68. And so I see a 1.51, maybe a 1.68, depending on what's going on. My iodine. Okay, if I look through here, I see, oh, here's an iodine right here, and it has a 0.54. But notice that it's over on this side. So that means I have to flip this. And why would that be? Because this is talking about reduction potentials. And so you see that it doesn't get reduced. It actually goes the other way. Okay, it gets oxidized. And so what does that give me? It gives me a number that's opposite of this. And by opposite, I mean this. It's a 0.54 if it's getting reduced, and that means that it's a negative 0.54 if it's getting oxidized. Okay, and so I can see those values as we go here. Now I take a look at nitrate. Okay, and nitrate is one that it's like, well, wait a minute, I don't see nitrate in this table unless I'm missing it somewhere. I'm not seeing nitrate. Oh, here's a nitrate. I see a 0.96. Okay, that means that it's going to be getting reduced, and so that number, a 0.96. Now I can think of this another way. Say you can't find it on this chart, and that's what I was kind of alluding to it because this is kind of a complex thing. I see a 0.96, but notice what's happening. It's forming a negative ion, just like iodine was forming a negative ion and so on. So we're looking at values of how much they like to become a negative ion. When I take a look at this and why that's important to just kind of recognize along the way with my hydrosulfuric acid, H2S. Well, I don't know what's going on there. I don't see that in any of the scenarios, but my H2S is going to form the hydrogen ion, in fact, two of those, and a sulfide ion. Okay, so the question is, what's happening? Well, what's happening is it's going to end up donating those electrons. If I go my H2S and it splits up, well, to balance this out, it's going to be donating the electrons there, making it a reducing agent. Okay, so it's kind of weird that way. This is a little typo. That should be Fe2 plus. And so I would just look that one up again, and that number is a negative 0.44. And the reason I know it's a negative 0.44 is because, let's see, that's a 3 plus. There's my 2 plus. I see that, sorry, that's a 0.77. But notice that, oh, actually, I am wrong. That is a 0.77, and that iron gets oxidized. It's a reducing agent. And so you just kind of watch those things along the way. I take a look at the reducing agents, I look at the oxidizing agents, and so on. So pretty straightforward as I kind of pull those things apart. Using your table, you'll have those at your reference, and so on. Now, where that table or why that table is important and why we needed to just see those things along the way is I can calculate the electricity along the way, the voltages along the way, just by using this very simple equation. The sum of the entire electrical current is going to be the product, the ending part, I should say, of the entire electrical current is where you have the voltage from your reducing agent plus your voltage from your oxidizing agent. Okay, so let's take a look at a scenario from this, and we're going to be again using, I'll just refer to the chart rather than bring it up again. You can find that and you'll have that at your hands along the way. We're going to use this for a voltaic cell where we have silver plus cadmium is forming the silver metal plus cadmium ion. Okay, so let's analyze this before I jump into anything. This is a +1, this is a 0, this is a 0, and this is a +2. Okay, so what's going on here? My reducing agent is my silver because you see that it's going from the plus, it's gaining electrons, and it's becoming my silver metal. And my oxidizing agent is going to then be my cadmium. And the reason is it's going from my cadmium metal, it's going into my cadmium 2 plus, and to do that, it's going to be giving off 2 electrons. Now, using my chart, I can add to this a little bit, and I see that my reducing agent, that ended up being, again, just using that, that was a 0.799, and my oxidizing agent value here was a plus 0.402. Okay, so just kind of take a look at it that way. And why that was important is because, remember, my energy of the entire thing is my reduction, and so that was a 0.799 plus my oxidizing, and that ended up being a 0.402. It's really important because sometimes you'll see the oxidizing, I've got to flip some things around for the numbers because I'm using a reduction table. But in this case, it's a pretty simple thing. On my voltmeter, I should read 1.201 volts. Okay, so in this scenario, if I was going to draw it out, now I can label up the parts. Now you can also see why I tend to show pictures that were pre-made of the entire thing. I'm going to attach my voltmeter here. This side is going to be my cadmium. This side is going to be my silver. And so what's happening is I've got my silver here, and I've got my cadmium here, and so let's see, what else do I need to include in here? That's pretty much it because my oxidizing agent and everything are already labeled. Cool. Now, it is, again, I just can't emphasize this enough. If I look on the table itself, that reaction is actually listed as a negative 0.402. But since I have to flip it because it says that if I have my cadmium 2 plus 2 electrons, that gives me my cadmium. Well, I have to flip the reaction because what's really happening is it's getting oxidized. This is going to be, this value that they give is my reducing value. And so I'll flip that sign as well. That's where my positive came from. Okay, so pretty straightforward with it. Just kind of watch how you use your tables and the information given. Okay, there's my table. And so there's a couple of points I want to emphasize along that. Make sure that that E value is always a positive quantity that's taking place in there. If it doesn't, then it's basically never going to go. It's what we call non-spontaneous. The quantities are independent of how the equation for the cell's reaction is written, though. You can never multiply the voltage by the coefficients. If you see those balance things, those aren't mole ratios to energy or anything like that. Watch out for those. But you can't just look at this and add up from that table either. You've got to make sure you figure out who's my oxidizing and reducing. So those are the general points I wanted to bring home of those. Now, I mentioned that term of spontaneity a couple of times. We got to figure out if something is going to be spontaneous by doing the math associated with it. If the calculated voltage for the reaction is positive, like I said, it's spontaneous. If you find your voltage ends up being negative, it's non-spontaneous. Okay, so let's apply that a little bit, and let's take a look at an example of nickel and the zinc. Okay, let's take a look at this and pull it apart a little bit. And once again, let's put it in terms of these cells. Okay, I'm going to be taking my my nickel, that's a solid, and I'm going to be forming my zinc. Okay, so here's my nickel, here's my zinc. I'm going to connect them up with a wire. I'm going to be measuring that voltmeter, and that's the question is, what will that voltmeter read? And so if I do this type of reaction, okay, so I've got my salt bridge in there, and what we're going to be seeing is it looks like my nickel is going to become my 2 plus, and it looks like my zinc 2 plus is going to become my zinc metal. Okay, so let's take a look at this. I saw this is a 0, this is a +2, this is a +2, this is a 0. So what's my reaction if I think of it in terms of a redox? Well, my reduction ended up being my zinc 2 plus as net. We should be getting pretty solid skills with all of this along the way. And notice that my oxidation is going to end up being my nickel metal, and it's getting oxidized this way. Okay, so now I've got those pieces. Now, that's all I need to do with it. If I was going to say that this is going to be oxidized, that makes this my anode, that makes this my cathode. Okay, my positive. Notice that it's going from my anode to my cathode, or actually the other way around, isn't it? My cathode's over here, and so we go this way with my electrons. Okay, cathode positive, anode negative, and so my electron flow is there, and so that means if this was sodium chloride, my negative side is here, my sodium is going to be here, and my chloride is going to be here. Okay, so there's my salt bridge. There's every skill that we had from that first unit now, or first section. Now, if I take a look at it in terms of this, I simply say that the E of my entire cell is the sum of my reduction plus my oxidation. Okay, so the E of my cell is what I'm looking for. Okay, so now let's take a look. My reduction is my zinc, and let's use our chart. And so let's look for zinc. And where'd my zinc go? My zinc ended up being a negative 0.762. Let's see, and my zinc on this side. Ah, right here. Here's my zinc. I was looking for that number. I have a little bit different number in here. That was a negative 0.762, just from the sheet that I had. Okay, and so from there, then I take a look for my nickel. And my nickel, I've got listed as a 0.236. So let's find that guy along the way. Here's my nickel. And notice right here. Here's my nickel. Now notice it's a negative 0.23. However, notice that the reaction is backwards, isn't it? It's being oxidized, and this is my reduction table. And so it is typically the energy of reduction was a negative 0.23. But notice what's going on. I've got to flip that, don't I? And so that negative becomes a positive. And so when I add those things up, what do I see? My energy, or the electricity, or the voltage, however you want to think of those things, ends up being a 0.526, negative 0.526. What does that mean? It's that negative in there. It means that it's non-spontaneous. Okay? It's not going to happen on its own. That's the key. All right, so taking a look, that was number 6, or example 6. Let's take a look at these things then. Let's take a look at it in terms of the next one on there is iron and iodine. Okay, my iron and iodine. Again, I've got the chart up there. Let's go ahead and process this one. All right, so with my iron and iodine, let's see, let's do a drawing. And let's just label up. And in this case, notice, I guess I don't have any solid metal in here. So remember the trick. If there's no solid metal, because we have the iodine, but that's not really a solid metal in there, let's go ahead and put in there titanium, something that is or platinum, or whatever, doesn't matter. We have some kind of metal in there that's not going to be reacting. That means, let's take a look at my iodine, and let's put my iron in on the other side. Okay, so let's break this apart in terms of some kind of redox reaction. Okay, so notice that my iron is going from a +3 to a +2. That means it's being reduced. It's gaining an electron. So I have 2 iron ions. Okay, and so that means that this is going into a 2+. And so to do that, I'm going to have to add 2 electrons in there. And why 2? Because I'm getting 2 ions in there. Okay, so that's where the 2 electrons come from. Now, that means that my oxidation then would end up being my iodines. I have 2 of those iodine ions, and it's going to form the iodine solid in there. And for that, I'm going to need 2 electrons, and that's given off. Okay, so if it's given off, that means that it's going to be oxidized. And remember that my oxidation end of things is going to be my anode. And this is going to be my cathode. Okay, he's going to give up an electron, he's going to be taking in electron. Where is it coming from? It's coming from the anode spot. Okay, so just kind of watch those things along the way. And now let's break this apart in terms of the energy. If I take a look at the reduction side of things and I look for my iron, okay, I see that I've got a 0.769 for that. And so here's my iron right here. Your book has a 0.77. And then we see also my iodine. I see that right here, and that is a 0.54. But what do you notice? I notice that this equation is flipped, which means that I've got to flip that number and make it negative. Okay, so my reduction end of things, that ended up being a plus 0.769 volts. And my oxidation, I have to put a negative 0.534 volts. Okay, so if I add those two up, what do I get? I get a 0.234 5 volts. Is it spontaneous? Yes, it is spontaneous because it is a positive value. Go ahead and include that plus in there. And so we've got those things. Now, this is kind of an interesting point. Notice that both of them are actually going to be taking in those electrons. They both have a positive value in here. And so just looking at those, it's like, wait a minute, what's going on? Well, what this is saying is that even though they both want to be reduced, what's happening in this equation is iron wants to be reduced more than your iodine wants to be reduced. And so really it's that's why the number is pretty small in here, is because they're pulling against each other. And so the iron is actually pulling the electrons. Which way is that going to be flowing for electrons? It's going to be flowing in this direction. Even though it doesn't want to, in this case, the iron is going to pull with more force. Okay, so that's pretty straightforward with those. Just keep track of the direction of things as we go. Okay, iron will oxidize to 2 plus by the treatment of hydrochloric acid. And again, the chloride can't be reduced here. It's only the hydrogen is only used. The chloride is not being reduced, can't be reduced. Is the reaction going to occur? Okay, so here's what we need to do with this, is we need to actually draw out, because here we've given you the equation. We've got to draw out the equation first. And so let's take a look. We have iron that's a solid, and we have then 2 hydrochloric acids. And the reason I've got 2 hydrochloric acids is going to become apparent right here, is because the iron is going to form the 2 plus ion, and that's going to be aqueous solution, and then I'll form my hydrogen gas. Okay, so let's take a look at charges. This is a 0, this is a 0, this is a -1, this is a +1, -1, +2. Okay, so we have the pieces on here. The net ionic, if I wanted to get rid of all these other things, in essence, get rid of those chloride ions, those are spectators, my net ionic is going to be simply this. Iron, that's a solid, plus 2 hydrogen ions, that's aqueous. And that will give me my iron, that's aqueous, and my hydrogen gas, that's going to be a 0 charge on there. Okay, so there's my net ionic. Gets rid of that chlorine, so it's a little bit easier to track. So let's take a look. Who's getting oxidized? So the iron is getting oxidized. And the reason it's getting oxidized is because it's going from a 0 to a 2 plus, and so I get 2 electrons off of there. Who's getting reduced? Well, that's going to end up being my hydrogen. I have 2 hydrogens there, and it's getting reduced because it's forming the hydrogen gas. Okay, so that's a 0. All right, so if I use my table, I see now that I know my reduction and my oxidation, now I can go back up to my table and take a look at my values. I see that my hydrogen, okay, if I take a look at the reduction one, there is a tipping point, and that's right here. Notice that tipping point, this is 0. And that reduction is 0.00 volts. Okay, now I take a look for my iron. And I see that my iron is a, let's see, that was iron 2. So I see a 0.44 there. It's a negative. Okay, but remember, this is a reducing table and it's oxidized. So I make that a positive 0.44. I add those up. I get my cell itself is going to be a plus 0.44 volts. Okay, so what that means is on my actual solution, I won't draw out everything here, that voltmeter should read somewhere around a 0.44, positive 0.44 volts. Will the reaction go? Yes, that's oxidation, or that is a spontaneous reaction. Okay, so that's how we would go about that type of problem. Draw it out first. I would go ahead and do a net ionic along the way. Now let's take a look at these. If we put those in with an acidic solution along the way, again, what the key to this particular type of question is, if it's acidic solution, we would see that the other piece, basically we're freeing up that hydrogen ion along the way, okay, in a net ionic solution. So I simply look at it and see, okay, there's my there's my hydrogen ion and so on. Will it occur along the way with chloride, iron, chromium ion, and iodine? Okay. If I do that, I kind of mix and match these other things. Okay. Now, here's another way that we could look at this. I could say, what if, will it occur when we mix them all up in an acidic solution? Well, I see that my iron will form the iron ion. I see that my iodine will form the two iodides. Okay. I see that my chloride will become chlorine plus 2 electrons. I see that my chromium will become chromium 3 if I add an electron in here. And I see that my iron, let's see, I've already written my iron in there. And so that iron could also form a plus 3 by doing this and adding that in. Okay? So the reason I split them up this way is if this is going to be reduced and this is going to be oxidized on these sides, if I use my values and I see that I have my iron, well, here's iron that's going from a 3 to a negative to a 2. Okay, so what's happening there is that 3 to a 2, that ends up being the opposite of what I see, and so this will be a negative. Let's see, I'm going, this one is saying a 3 to a 2, and that's going to be a plus 0.77. But this, if it goes the other way around, actually if I look on this side, if it goes to a 2 to a 3, that ends up being a negative 0.77, doesn't it? If I go my 2 to the iron itself, okay, that's let's see, where's an example of that one? That's going to be right. Where's my iron? Here's my 3 plus. There's my 2 plus. There's a negative 0.44. Okay? So there's a couple of things that can happen with that iron 2 ion. If I take a look at my iodine, okay, my iodine, we saw that one previously, and so I see a 0.54 there. But notice I'm going I2, so that's a plus 0.54. And I take a look at my chloride. Okay, and so where's my chloride ion? Let's see, it's going to be right here. Notice my chloride ion. That's negative, but it's a product here. I got to flip this sign, don't I? A negative 1.36. That's because it's oxidized. And lastly, I've got my chromium to deal with. And that one is going to be right. Let's see, and that is a chromium 2. So there's my chromium ion right here. A negative 0.54. Oh, I've got to change that, don't I? Or 0.50. Here's my chromium ion. So that's going to be a plus 0.50. And so I take a look at the game, and I see that which ones are going to be going on. I basically just mix and match. My 0.44 to 1.36. Okay, that's going to be a negative. That's no. What if I took a 0.44 plus this? Oh, that's going to be positive, so this is going to be a yes. That's going to be spontaneous. A 0.44 minus, nope, that's not going to be. That's going to be a negative. I take a look, 0.54 minus, nope, that's a negative. Here's a positive, my iodine with my chromium, and that's going to be a negative. So there's only two cases where it's going to be spontaneous. So those two cases are going to be I2 plus 2 electrons. That will form the 2 iodine ions. And I have my 2 chromiums. And that's going to form my 2 chromium 3 ions and 2 electrons. And so that value ended up, and I'm just going to use the numbers that I've got, not necessarily with your table there. That's fine. A 0.408. And this one ended up being a 0.534. Okay, if I do that, I end up with a total scenario of 0.942 volts. There, I've got to add them all up in there. Those are the only combinations that are going to be producing a positive E value. And so there's what's going to happen when I mix all those things in the acidic solution. Whew, that's a lot of stuff. But basically, you just kind of keep the math straight, use that table, and you should be in pretty good shape along the way. We should be able to do now assignment number 2. We will be doing a quiz on this to take a look, and we'll be taking a look at some things. And very soon, we're going to be actually measuring that electricity when we make our own batteries. All right, you guys take care. Good luck.